Okay.
Cool. So, hi everyone. Good afternoon. So, for our next speaker, we have Paul Stoy from the University of Wisconsin-Madison. Paul is a professor of biological systems engineering at Madison. He did his undergrad also at UW-Madison and then went on to do a PhD at Duke University with Gabby Cuttle and did a postdoc at the University of Edinburgh. He was a faculty at Montana State before joining Madison. And at UW-Madison, his research group focuses on eddy covariance fluxes, ecosystem ecology, remote sensing, and regional climate processes. And now he will talk to us about bridging the link between flux stars and models to enable upscaling. Good to have you, Paul, and yeah, please go ahead.
Hi, Serena. Thanks so much, Bailey, and all the organizers. Thanks for the invitation. Thanks also for the flexibility. I wasn't able to make my originally scheduled presentation yesterday. I was actually on the way back from doing field work in California at an eddy covariance site. So I'm going to explain to you the Alive project that we've been working on. And so when it comes to that work, I'd really in particular like to thank Danielle, Sadeg, Sophie, who have been instrumental in organizing data sets, putting together workflows, and doing the machine learning that comprises Alive, as well as a number of the people who've been extremely helpful, Inara, Ely, Bethany, Ojaswe, Encore, and funding agencies from a number of different organizations and data from Ameriflux and also Neon. And thanks all of the PI contributors to the Ameriflux dataset because we use it all the time. And so the other thing that this project is a little bit of a part of is a project that is funded actually by Google called Benchflux. And so Benchflux is really trying to better understand at multiple scales, right, these ecosystem processes, ultimately for societal benefit and also to estimate uncertainty, right, in these fluxes across space and time to better reduce uncertainties and to better understand these carbon and water fluxes upon which we all rely. So some of this talk came from a presentation that I gave in Germany earlier this summer in a place that was close to where a famous philosopher and writer named Goethe um, used to work and live. And one of his famous quotes is, Es ist nicht genug zu wissen, man muss auch anwenden. And what this means is, in translation, knowing is not enough, we must apply, but it's really not a very good translation, that typical translation. What he's really talking about is like turning things toward like changing things. Anwenden means really to like move in a new direction. And so what I'd like to think about is how can we take the upscaling work that we're doing, the carbon fluxes that we're measuring, the remote sensing that we're doing, and make it even more useful, not just to ourselves as scientists, but also to society. Then we can also think about other famous flux philosophers like Dennis Baldacci. And paraphrasing, he said one time, measure flux everywhere all the time. And that was something I was at the conference when he noted this. It was just probably down the hill from where I think you are in Berkeley. People in the audience were a little skeptical, but honestly, with all of the observing systems that we have now, we can kind of do this. And the question then becomes, right, how well can we do? How can machine learning help us out? And how can we communicate these everywhere, all the time observations effectively to the public to improve management? So, to get even more back into thinking broadly about what we do as scientists, is we usually learn from the past, we build our models, we train them on past data, we predict the future, and we may or may not be doing a particularly good job. This famous uh, figure by Friedlingstein many years ago demonstrates the spread of land carbon uptake of different models, right, up to the year 2100. So we're usually thinking about the past and the future in flux science. But meteorologists are always thinking about the present and the near term future. And so, can we think of perhaps Janus, like that last slide, looking backward and forward as being our scientific motivation, but someone like Zeus, the god of weather, being our motivation for understanding things that are happening immediately. And I'd like to argue that this might be more of an engineering problem and a workflow development problem than a scientific problem per se. If we have the observational systems, how do we connect those systems, right? How do we build those things like an engineer might to get a better estimate of real-time fluxes? And then the challenge becomes, right, can we combine our knowledge and our engineering skills to understand the past and the present and the future of the carbon and water cycles? Or by doing so, are we making something that we are going to have a difficult time controlling, right? That we can't really do all things well? Or are we going to do one or two things well at the expense of something else, right? Are we not going to be able to do things equally as well? So these are things that we have to think about because if we're really trying to bring all of our knowledge together, right, we want to do something that is effective, where uncertainty is accurately communicated, and that we're not, right, saying the sky is falling, but at the same time, we're aware of the risks that are occurring. And so this is kind of a little bit of the background of what we're trying to do in Alive is try to take observed eddy covariance fluxes, right? Connect those with geostationary satellites, so weather satellites. And we've built a large database of all of the tower carbon water fluxes, as well as the geostationary satellite observations. And we've combined them in a machine learning model to create near real-time predictions of carbon water fluxes. And what does that mean? That means this is yesterday's estimate of GPP. So this is every 5 minutes. This is using our weather satellite, our machine learning model that's based on eddy covariance observations. There's reflectances. There's a lot that goes into this, right? But you can see the impacts of clouds. You can see something that I noticed. I don't know if you can see just in the middle of Florida, a little bit to the south of the middle. There's a spot that'll show up as really bright orange, meaning big, like yellow, meaning big carbon fluxes. That's where most of the sugarcane in the U.S. is grown, right? That's a very productive agricultural region just south of Lake Okeechobee. So you'll be able to see a lot of dynamics that occur on a sub-daily basis. And this should just loop itself again. Is it looping? Yeah, here it goes. It's nighttime now. No, it stopped looping. Why did it stop? Well, either way, something happened. It should be going again. Here it goes. Come on, you. So yeah, so you can see the dynamics that are emerging throughout the course of the day. You can see places where there's a lot of carbon flux, places like near the deserts of the West where there's very little carbon flux. In California, there's more again because it's been quite lovely there. And places like the Yucatan in Mexico and Cuba, it's also a pretty nice time for a plant to grow. So how does this work in practice? Really, we're taking observations from Google Cloud. These are satellite observations and estimates of surface reflectance, and not just NDVI. We're using, and not only NIRV, but we're trying to add shortwave infrared reflectances to our machine learning model. We use an XGBoost model. We use the shortwave because it helps. It has something to do with water. We're not really sure the mechanism, but we try to do our best to use the best aspects of the geostationary satellite. We consistently find that gradient boosting models are kind of the fastest and nothing is better than them. They're a little, they're certainly very fast for the purpose at hand, which is to create these near real-time predictions. We add these to growing czar libraries that live in cloud optimized S3 buckets online, and people can access these and you can do science with them. And right, we're trying to create a pretty light workflow where everything happens quickly because we're trying to do our simulation every 5 minutes. We're also, as you can see in this little slide here, we're adding more to it. At the moment, we are only working with the geostationary satellite, but we're adding near real-time observations of meteorology via the high resolution rapid refresh. And that's what I'm showing here in the bottom right, where this is the it's a weather model that also creates near-term forecasts, and it has near surface temperatures and radiation and other things that determine the fluxes. We're also adding those to our machine learning model now. So we're actually moving from our previous estimates every 5 minutes, which is a little bit much, to every hour because that's the time step of the HER, and are moving down from 2 kilometers to 3 kilometers because that's the native resolution of the HER. So we're trying to add some surface meteorology to get better real-time estimates of fluxes because the satellite alone can't see important things like vapor pressure deficit that we know are important for flux determination. So This is how the whole thing works, and we're working hard on water cycle aspects as well. This should say latent heat in watts per meter squared. This is like an earlier estimate that we had, just kind of a proof of concept that we can integrate both the geostationary satellite and the high resolution rapid refresh to get a combination of the satellite imagery and the meteorology to estimate water and carbon fluxes, kind of almost as they're occurring. Right. So this is kind of really what we're motivated to do is create something that's tangible that we can potentially use, right, to connect the science that we're doing to people who are managing ecosystems. So I want to mention as well, right, that this geostationary satellite remote sensing of carbon and water fluxes is not new. People oftentimes use MODIS, they use Landsat. These are fantastic satellites. There's a latency of a few days or more. In the case of Landsat, a couple weeks. And we really, yeah, can you hear me? Oh, sorry, I thought I heard something. I hope you can hear me okay. But I wanted to mention that, right, for a long time, people have been using these weather satellites to estimate evapotranspiration. And also Martha Anderson has a paper where she was using them to measure, estimate really carbon fluxes as well, using a very kind of physical approach to do so. So if we're really trying to combine the past, present, and future, at the moment, right, we only have the empirical data. Our machine learning model is just putting patterns together. We want to move toward knowledge-guided machine learning. We want to incorporate physics. We want to incorporate the things that we know about how ecosystems work. So really the challenge here is not just to let a machine decide how fluxes work, but to bring what we know about fluxes, right, and what the machine thinks together to have a better constrained estimate of what's happening. So this is our push toward knowledge-guided machine learning. And we're doing so, we're starting with the challenge of understanding not just the total amount of water that's going from the surface to the atmosphere via evapotranspiration, but trying to understand the components of evapotranspiration separately. So we have transpiration, which is going through the plant, through stomata, unless you're a moss. And it is basically, right, coupled to the carbon cycle via canopy conductance. There's also evaporation from plant canopies, which is helping cool the leaves, but is not directly being used in that, canopy conductance where carbon can also enter the stomatal function. And there's also soil evaporation, right? So if we're really to understand the global change impacts on the water cycle, we'd like to understand these terms separately because global change impacts are changing these different components in different ways. Transpiration, notably, of course, is also under biological control, whereas the evaporative terms are under physical control. And transpiration is also under physical control. So how can we get at that? What we're trying to do is get more information from eddy covariance. And this is where neon has been particularly useful. So if you have the high frequency eddy covariance data, the stuff that we're measuring at 10 or 20 hertz, right, every little eddy, there's been a number of approaches, flux variance similarity, conditional eddy covariance. We have been using conditional eddy accumulation that are essentially using, and this is a nice quote from Narazan, carbon, the CO2 molecule as a tracer to estimate water sources. What happens in effect when you have a little eddy and that eddy has less carbon dioxide but more water vapor than the surrounding air and it's moving out of the ecosystem, that must have interacted with the canopy, right, to have that net photosynthesis that took the carbon away. If you have that eddy vary that's going up and it has more water vapor concentration and more CO2 concentration than the surrounding air, that must have interacted with the non-photosynthesizing surface. Okay, so you can put all these eddies together and kind of, right, understand where they're coming from, where their source is, and use those to estimate the different sources of water, either the surface evaporation or transpiration. What it can't really tell you is if it's coming from the similar source in the canopy, if it is transpiration or intercepted evaporation. But we know things about interception, right? If it rains, the leaves are going to dry out pretty soon. Okay, we can make some rules about when these different processes can and cannot occur. And we can therefore partition canopy intercepted evaporation from transpiration and surface evaporation. And we went ahead and did this by providing some rules to a knowledge-guided machine learning framework. So when you take all of the neon data and this data set, I'm going to flip back 2 slides that Anarazan and others put together, where they've taken all of the high frequency eddy covariance data from neon and they've created an open data set of evaporation and transpiration. We basically use knowledge-guided machine learning to further partition that in a current preprint into transpiration, surface evaporation, and intercepted evaporation. And we just gave the machine some rules. We said, well, if it's been more than 24 hours after precipitation, can it better be dry? Let's say 8 hours after dew fall, or when there's a crossing between the dew point temperature and the air temperature, let's not train the model in those periods. So we basically train the model during periods when we know the canopy is dry and EI has to be 0, and let the machine then figure out what the other terms are. So we have kind of dew deposition as a negative term, all the other fluxes are positive, and what the machine effectively does is say intercepted evaporation is mostly 0 unless there's some right uh, rain or dew that just fell. And you can see the distribution of the transpiration and the surface evaporation. So we've now put all of these fluxes together, and we're going to use those to kind of across the US estimate these terms separately. We still had some questions about where we should take that intercepted evaporation. We take it from the canopy, from transpiration, instead of from the surface evaporation term, because that just simply gives us a better fit when we're comparing these against the observations. The model is also happiest when we do that, and we get a relatively high R squared for our um, learned evapotranspiration versus that from conditional eddy accumulation for all sites except for some that are like up in Alaska, where we think that there's a little bit more going on with the water cycle, including like standing water and other things. So what we're going to do, this is the same figures before, is add these separate transpiration, surface, and intercepted evaporation terms into Alive, right? We'll also, of course, predict things at night. Right now, there's like a nighttime window that's crossing this, but we're going to take that away. We're also trying to couple these with the carbon fluxes using even further knowledge-guided machine learning approaches to use the coupled carbon water cycles as additional constraints to feed the model to have it provide more robust predictions of land surface fluxes that we can then try to communicate in real time. The other thing that we're trying to do going forward, right, there's new geostationary satellites coming in the 2030s. We'd like to see how useful these things are for yield, drought, phenology, trying to get these rapid changes to carbon water fluxes better simulated, but also better predicted. The thing that we're working on right now with an NSF proposal that I hope goes forward, and I hope you can see this, I think that you can, is really this idea that there's a explosion in AI enhanced weather modeling right now. Every time I go back to this proposal, there is, it seems, a new and better AI enhanced weather model. There's WeatherNext, right? There's ones from NVIDIA called ForecastNet. There's ones from the Chinese called Pangu. There's US agencies are putting them out. It's amazing how well these models, these weather models are doing up to 2 weeks in the future, just by learning patterns. And so if we take that weather forecast and we also essentially forecast surface reflectances, right? Like your the things that go into your NDVI, although we use different variables in NDVI, we can get a 2 week out forecast of carbon and water fluxes. Will that be useful for understanding phenological events and changes? Will that be useful for understanding when to irrigate? Will that be useful for understanding when there might be a flash drought that's emerging, right? Can we actually forecast disturbances to the coupled carbon and water cycles by putting essentially a forecast model of our surface reflectances together with an AI enhanced model of the weather. And exactly how to do that, we basically are working with either a SWIN UNet architecture effort is what we're trying to propose, or a graph neural network, because those are the two fundamental ways in which the weather models are working. So we can basically predict surface dynamics like the AI enhanced models are predicting the weather, bring those two things together, right, and create an even better estimate of the near term, hopefully useful fluxes. So that's really what I had for everybody. I hope I'm not going too far over time. And there might be some time for questions. I hope that there is because you guys seem like a great group and I wish I was there. And yeah, thanks so much also again for your attention.
We have some time for questions if you don't mind answering a few.
Yeah, I'm here.
Could you say a little more about the physics-informed machine learning and what kind of processes it's being constrained with?
Which machine learning?
The, I can't remember if you used the term physics-informed or.
Oh, yeah, right now we're using knowledge guided machine learning. And so I the thing that I failed to do is I didn't put the preprint up here because this is something that we've submitted already. Yeah, but we can Sadegh Ranjbar is the one who put together this architecture. And it's basically using a knowledge-guided machine learning approach. It's just giving the machine a number of rules that it has to follow. So it doesn't natively know the physics. This isn't really a hybrid model like people have been calling them. This is simply providing like constraints. So one of our constraints, ET equals T plus ES plus EI plus deposition, is our version of a water mass balance. But there are a lot of people who are doing some really cool work with hybrid modeling, which is essentially using machine learning to help guide a physics constrained approach. And that's how a weather model I'd like to think will most of the time be working. Although I don't actually know about the details of the architecture for those. I only know the techniques they tend to use. But those are really good questions, right? This is kind of, I think, where we're at right now, where a lot of people are basically using machine learning to enhance existing and very successful oftentimes ecosystem models. We're kind of starting from the empirical end and slowly kind of telling the machine a little bit more what to do. Um, and this is kind of a little bit my philosophy, not to get too philosophical, is that I feel oftentimes with ecosystem models, we're like telling the ecosystem what it's doing. And the thing that's been fascinating with me about machine learning is that we can use it to help us listen to what the ecosystem is trying to tell us and not say, if your NDVI is this, then you do that. Right. So one example for us was listening that the shortwave infrared, these reflectances, in our case at about 2200 nanometers, tended to be very important for better predicting surface fluxes, at least from the geostationary satellite. So, we kind of created a new index that incorporates this shortwave infrared. So we're trying to use machine learning in a kind of a deferential approach, if you will, and see if we can't use it to help guide us in understanding what ecosystems are trying to tell us with the data. And so hopefully this is a nice compromise or nice um, kind of not contradiction, but alternate route for others who might be using a more physical model and then using machine learning to help guide parameterization or help guide the physical model construction, which are also super cool things to do. And there's tons of great techniques, including, for example, symbolic regression to help kind of learn the best mathematical expressions that are underlying particular data sets. So it's a super exciting time to be in all science right now because there's an explosion of techniques that I'd like to think we can really use to help figure out how ecosystems work and really like reverse engineer their behavior. But really good question. Thanks for it.
Thanks, Paul, for the talk. So I was wondering, have you ever tested your partitioning T with traditional partitioning methods using neon science?
Traditional methods. So that's a really good question. We really The answer is no. But it might be good to I've so kind of the challenge, and this is an important challenge, is that when you do this type of work, like the partitioning of the water vapor using flux variance similarity or conditional eddy accumulation or other approaches, conditional eddy covariance, and you compare them against sap flux or against like soil collars or other things, that they don't really match. And we already knew that. And there's also not really sap flux. It'd be interesting if they had more sap flux in neon to compare. The other thing that we really rely on from eddy covariance is that in principle, right, if the system is connected, it can send you the data and have your fluxes computed also in near real time. And so you can bring those eddy covariance data streams kind of into your model, and you can even have the model auto update as it's learning new from the fluxes. So we really love eddy covariance from that perspective. Like Anchor Decize Group is one of the few that's actually streaming data and calculating them all the time. Neon, there's like a 2-week lag, but we could actually use that and kind of build up from it. So the the short and long answer is no, but a better answer might be that it would be really interesting to compare our predictions against other techniques, including isotopic techniques, including lysimeters, including the other things that people have. We're just using this approach because it gives the machine lots and lots and lots of data, right? And the machine just loves the data. So that's where these ET partitioning schemes come in, to me, extremely handy, just because there's so much of it. Yeah, but I like the question.
I have one question. Thank you, Paul. So you are talking about the large what's weather prediction models for the weather prediction, and now you are trying to learning the reflectance from these models, like the prediction or projection for the next 2 weeks. But for the weather prediction models, they are trying to learn something like the dynamics or moving across pixels. But the reflection is stable on the pixel, right? It's only temporal changes. There's no spatial mix.
Yes and no. So the ones that use a transformer-based architecture do have a little bit more of that spatial constraint, although it's not, in my understanding, really the eddy physics. It's just something where it's able to look like weather. But I know what you're talking about. There's a huge essentially risk. I mean, we don't know the future. We never will. Of the model really not working. It simply has learned, especially in an era of global change, it's simply learned on past patterns. So there's fundamentally, in my emerging understanding, kind of the transformer-based approach, and that's where the SWIN UNetR approach is going to come in handy for us to try to test versus like a graph neural network approach. The other thing, the challenge with us with like a graph neural network approach is that it only really needs to be properly initialized and it can just forecast however. It doesn't really require any sort of ecosystem memory. Or it might not be the best for simulating the impacts of past conditions on future ecosystem behavior. So we think that we need to have a transformer type model that can go back pretty far in the past to try to simulate how reflectances are going to emerge in the future. But people have used graph neural networks to forecast like NDVI in certain ecosystems. So people are starting to really, from an ecological science perspective, use machine learning for ecological forecasting. I think that there's going to be a lot to learn in this domain because right now we're just writing an NSF proposal that's essentially hypothesizing the best machine learning architecture for the challenge of surface reflectance prediction. And we have hypotheses, and as we know, we're probably going to find that our initial ideas aren't going to really work. But I think it's kind of an important direction to go because what everybody wants, like your farmers, your land managers, they want a crystal ball. They want to be able to see in the future. And the weather models can see to a shocking degree at least 2 weeks, if not a month into the future. Can we do the same for the carbon and water cycles? And the answer is eventually going to be yes. And I think that there's going to be a lot of exciting new techniques that are going to emerge and are already emerging like in this domain. So it's I I basically think that we can forecast flash drought. Is if you had to ask me what I'm actually trying to say, I think we could actually figure it out. Yeah.
There is one paper from ETH. They already did some tests to use the weather forecasting model to do the hydrology prediction for ET and runoff prediction.
Okay, yeah, if you could please send me that. The thing that's exciting about this is that really like every week there's these new papers coming out, and so I'm trying to write this proposal, and like every time I go back to it, there's like a new weather model or there's like a new reference site. It's really a lot happening right now, which is very exciting, but also very daunting.
Thank you.
Thank you. Thanks for noting that new paper.
Do you have any
Go ahead.
other questions for Paul? No?
Maybe a quick question. Hi, Paul.
Yeah.
Regarding your new method, so how was the performance regarding some extreme condition, like maybe dry or wet condition? Does it work well?
Once again,
How about the performance of model? Your model working on the extreme condition, like dry and wet condition.
yeah. Okay, this is a great point. So what happens, of course, is that the model simulates the mean and has a hard time with the extremes. I feel like, at least in our paper in remote sensing environment with Lossos et al., we think that Alive can do a pretty good job simulating the rate at which ecosystems are responding to something like a flash drought that emerges. And it can see very clearly what's happening like before and after a hurricane, because it can see like, you know, the reflectances before and after. So you can get good inference pretty quickly. It works. We did a comparison against Bess and Modis in the paper for flash drought simulation, and it tended to say that things were happening more quickly with the flash drought, and also that things were not as bad as you might have, as some other models, as the other models thought when it came to like the flash drought severity. So I think like all machine learning models, the more extreme events it's trained on, the better it will do. We're constrained in time because, you know, geostationary satellites didn't provide the products that we use since starting in 2021. And so we don't have a huge long time series on which to train it. So for simulating extreme events in a machine learning way, if it sees those extrema, it can probably learn to predict it. And if it's never seen it before, it's going to be out of training. So there's certainly room for improvement, and a lot of that improvement is simply just from the data availability side.
Thanks.
No, that's a good question too. Thank you for it.
All right, well, thank you again,
Cool.
Paul. It was a really great talk. and we
Thank you.
appreciate-
Yeah, it was great seeing you too. Great seeing everyone. Thanks so much for the questions. Hope to see you at AGU or AMS or similar. Appreciate it. And I'm gonna stop sharing. All right. Bye everyone. Oh, and please don't hesitate to write if you have any more questions or anything, because I'm available. Thanks again.
I will leave.
Okay. This is Srinath, everyone.
Hi everyone. Nice to see you all virtually.